Welcome to INSITECT. Today we are talking about emergency evacuation systems, technology, and compliance. When you walk into any modern large building, a hospital, a skyscraper, an airport, you are surrounded by a silent, complex network designed to save your life. Most people still picture that old screeching fire bell, but the sources we've gathered for this deep dive reveal that modern emergency evacuation systems are just exponentially more complex. This isn't just an alarm. It's a critical interconnected infrastructure, a true convergence of security, IT, and, well, core life safety mandates.
It really is the difference between a shout in the dark and, say, a GPS routing system for crisis management. The platforms protecting occupants today are highly engineered. Our mission for you, the listener, is to analyze the core technologies, the complex architectural principles that ensure reliability, what we call fault tolerance, and the stringent compliance standards like EN54 and NFPA 72. These codes govern how these platforms coordinate everything from the initial alert to communication, and most crucially, the controlled movement of thousands of people.
I think we should establish a theme right out of the gate here. We're really looking at the shift from chaos management to coordinated control. So let's unpack the core technological driver of that shift, because the move from an abstract alarm bell to specific guided voice instructions that fundamentally changes human psychology during a crisis.
That takes us directly into the realm of voice evacuation systems, or VES. What is pretty simple, really. VES uses integrated networks of speakers and visual alerts to deliver clear, intelligible voice messages, replacing those abstract sounds.
And the why is profoundly behavioral, isn't it? If a generic alarm blares, the first thing people do is look around. They check their phone. They wait for some external confirmation. That delay is deadly. But if a calm, authoritative voice says, "Attention, fire condition detected on the 3rd floor, exit the building immediately using stairwell B," you eliminate that hesitation.
Precisely. The psychology is straightforward. Specific instructions guide people towards safety through coordinated egress routes. It imposes predictable patterns on a highly unpredictable event, which is the key mechanism for reducing confusion and preventing the kind of cascading panic that often makes emergencies so much worse.
So if the voice messages are pre-recorded and location-specific, how does this system, the operational brain, know exactly what to say and to whom?
That's the job of the Voice Evacuation Control Panel. It functions like a mission control hub. It receives inputs, say, an intelligent smoke detector on the west wing registers smoke, and it immediately executes a pre-programmed crisis response. That sequence then triggers targeted announcements for that specific zone, while maybe issuing different preparatory messages to adjacent zones for a phased evacuation.
That makes a lot of sense. But how does the system coexist with, normal daily life?
Yeah.
In facilities like schools or hospitals, they already have massive public address systems running general announcements. The sources talk about PAVA integration.
That integration is a practical necessity. It's about efficiency and cost, allowing the public address, the PA, and the voice alarm, or VA systems, to share the same speaker infrastructure. However, it introduces a necessary conflict that has to be resolved through mandatory priority logic.
Okay, so what does that priority logic look like in practice?
It means that routine announcements, like "Dr. Smith, please report to surgery," must be automatically and instantly overridden. They're silenced when a critical alert, like a fire alarm activation, is detected. Standards like EN5416 strictly define this priority handling to ensure life safety always takes precedence over operational communication.
Now, if we look beyond fire, and the sources making clear these systems have extended far beyond just fire detection, we get into mass notification systems.
Yeah.
What specific standards govern that expanded capability?
Well, mass notification essentially turns the fire alarm infrastructure into an all-hazards communications platform. This extended functionality, covering security threats, chemical releases, or severe weather, brings in additional standards like NFPA 72 and UL 2572. The system has to be able to handle diverse input sources and transition the facility from normal operation to a crisis response based on preset scenarios.
Okay, let's move into the structure itself. If the message is clear, the system then has to ensure the actual movement of people is coordinated. This leads us to the crucial architectural concept of zoning and phased evacuation.
This is absolutely fundamental, especially in large, complex facilities. Zoning divides the building into manageable areas, usually aligned with structural fire compartments. This isn't just about setting off alarms, it's about controlling the flow of people.
Why is controlling the flow so critical? I mean, my intuition would say the fastest way out is always the best way out.
Because in a high-rise, for instance, if every single person rushes toward the stairwells at the same time, you create immediate catastrophic congestion. Phased evacuation strategies prevent this. Only occupants in the immediately threatened area, say floor 20, evacuate first. Occupants on floors 19 and 21 might get a prepare to move alert, while those further away get a shelter in place command.
So the zone design, married to the voice system, empowers incident commanders to selectively direct actions, optimizing stairwell capacity.
Absolutely. And that strategic movement relies entirely on effective route planning. Evacuation plans must detail not only primary routes, but also designated secondary routes for when the main paths become blocked.
And we can't forget accessibility here. The planning has to include areas of rescue assistance.
Correct. The plans mandate refuge area communication systems. These are usually two-way communication devices that allow individuals with mobility impairments to maintain contact with the fire command center. This ensures they are constantly accounted for.
Let's talk about the technical backbone that makes this simultaneous, synchronized communication possible. The sources cite digital audio networks like Dante or AES-67. What's the fundamental advantage of using networked IP infrastructure for this?
It's all about speed and synchronization. These protocols are the digital pipes for the system's audio. They transport uncompressed, high-fidelity audio over standard IP infrastructure.
And if we had to pick one key performance metric that defines success here?
Latency. You need assurance that the message hits every single speaker at the exact same moment. Modern digital audio networks achieve extremely low latency, often quoted below 5 milliseconds. This ensures perfect synchronization across all zones, preventing confusing echoes or staggered warnings that could cause people to second-guess the instruction.
Okay, here is where my skeptical hat comes on. We've established that we've gone from simple wires and bells to these highly sophisticated systems, control panels, digital audio networks, software, routers. Isn't this complexity inherently introducing far more single points of failure than the old mechanical system ever had?
That is the most critical challenge facing modern life safety engineering. And the answer is yes. Complexity introduces risk. But the standards mandate a response. The entire architecture is built around fault tolerance and redundancy that vastly exceeds typical commercial or IT infrastructure requirements.
Tell me how that redundancy is physically achieved in the components.
Okay, let's start with the operational brain, the control panel. Critical components use what are called hot standby configurations. Think of it like a co-pilot who's flying the plane right alongside the main pilot. The backup controller constantly mirrors the primary system state in real time. If the primary unit fails for any reason, the backup takes over instantaneously. There is zero interruption to ongoing announcements.
That's controller redundancy. But what happens if the power grid goes down, which is pretty likely in a major incident?
Power redundancy is non-negotiable. Dedicated uninterruptible power supplies, or UPS, and massive battery banks are mandatory. The European standard EN544 specifies minimum requirements. The system has to handle 24 hours of standby time, followed by 30 minutes of full alarm operation.
24 hours of standby, then 30 minutes of maximum volume output.
Yeah.
That sounds like an enormous power draw. How is that even managed using batteries?
That's where the specific technology of the amplifiers comes in. These systems rely on high-efficiency Class D amplifier technology. These operate at, say, 85 to 90% efficiency, meaning they waste very little power as heat. Maximizing that efficiency is the only way to manage that huge power load and still meet the mandated battery duration without needing a battery room the size of a garage. It's a key engineering trade-off.
That detail is brilliant. So optimizing efficiency to meet a strict compliance timeline?
Yeah.
What about the wiring connecting the speakers? If a speaker wire is cut, say, by the fire itself, does that entire line go silent?
Ideally, no. This is handled by wiring redundancy, specifically the use of Class A loop configurations for the speaker lines. Imagine a wire that runs out to all the speakers in a zone, but then loops back to the amplifier rack.
So it's connected at both ends.
Exactly. This is circuit redundancy in action. If there is a single break in the line, a short, a cut, whatever, the audio still reaches all the speakers through the remaining intact path of the loop.
That establishes a framework that is engineered to fail gracefully. But let's move beyond the hardware. The most robust system is useless if the message can't be heard clearly. This brings us to the intelligibility hurdle.
Yes. You can have perfect wiring and perfect redundancy, but if the message is garbled due to poor acoustics, the system fails its core mission. Standards like EN5416 for control equipment and EN5424 for loudspeakers define strict performance parameters to prevent this.
The metric used in the sources is the Speech Transmission Index, or STI. For listeners, what does STI actually measure, and what's the threshold for safety?
STI is the objective measurement of message clarity. It quantifies how reliably the spoken word is transmitted and understood, ranging from 0, which is unintelligible, to 1, perfect clarity. Think of trying to understand an announcement in a bustling airport or a high-ceiling train station where the acoustics are just terrible. That's what STI aims to combat.
I think we've all been in that airport or massive stadium where the voice sounds like Charlie Brown's teacher. There's an announcement, but you can't make out a single word.
And that experience perfectly illustrates the problem. To achieve compliance, facilities must achieve an STI value above 0.50 in all protected areas. This demands meticulous acoustic design, placement of speakers, and verification testing.
So it's not just installing equipment, it's proving through rigorous testing that the audio quality is maintained across every square foot of the building. How do we ensure that functionality doesn't degrade over time, maybe if a wire gets nicked or a speaker fails?
That's where continuous health checks come in, a key feature called line supervision. The system is designed to check its own pulse constantly. It monitors speaker connections using low-frequency pilot tones.
Wait, pilot tones? Are these audible?
No, they operate at a frequency that is completely inaudible to us. They are electrical pulses used to measure the circuit impedance. They're testing the physical integrity of the wires all the time without bothering anyone.
That is essential predictive maintenance.
Exactly. If there is an abnormal impedance reading, maybe a speaker coil has degraded or a wire has started short, the system instantly flags it as a trouble condition. This alerts maintenance to fix the problem before an emergency occurs.
This all relies on a foundational rulebook, which the sources call cause and effect programming. If the hardware is the body and the network is the nervous system, this is the brain's logic.
This is the most essential and often customized step in commissioning. Cause and effect programming defines the rules. Precisely which fire conditions input events trigger which output responses. The matrix maps detection zones to specific announcement content.
And lastly, compliance has to ensure the message reaches everyone. This mandates rigorous accessibility compliance.
Correct. The system must notify all occupants, including individuals who are deaf or hard of hearing. This requires integrating visual indicators, strobes, and beacons. A crucial detail here, mandated by standards like NFPA 72 and the ADA, is synchronization.
Why is synchronization so important for visual alerts? Why can't they just flash independently?
Random, uncoordinated flashing across a large space can cause severe disorientation and even trigger medical issues. They must flash simultaneously within a very tight tolerance to safely signal the emergency without adding to the hazard.
Bringing all these layers together, from the psychology of voice evacuation through all the redundancies to the continuous monitoring and verification, it really synthesizes the strategic value of modern systems.
The strategic value is that modern evacuation is fundamentally about managing complexity through automation. It requires deep integration, often via APIs and SDKs, with every other major building system. HVAC must shut down, door locks must release, elevators must recall.
Let's discuss the architecture of control, especially with modern management techniques. A lot of platforms use cloud-based dashboards for monitoring. What's the operational requirement for a life safety system when it comes to internet connectivity?
The requirement is clear. A hybrid architecture is mandatory. While the cloud is excellent for remote maintenance and diagnostics, the core life safety system must never, ever rely on an external internet connection to execute a life-saving sequence.
So the on-premise controllers must have complete autonomous operational control. If the fiber line is cut, the evacuation sequence still fires instantly.
Absolutely. The technology is designed to operate regardless of the status of the broader digital environment. Reliability and autonomy are the highest priorities.
So if we synthesize everything from the high-efficiency Class D amplifiers to the rigorous STI testing, the takeaway is that a successful evacuation system is an engineered consensus among IT, security, and fire safety codes.
And its strategic value is that it transforms a moment of crisis into a managed, phased operation, saving minutes that save lives.
Here's the final provocative thought for you, the listener, to mull over. We've established that the hardware is incredibly robust, featuring hot standby controllers, power redundancy, Class A wiring, all designed to combat technical failure. But if the technology itself is engineered to be practically invulnerable, the effectiveness of the system ultimately relies on the quality of the programming, that cause and effect matrix, and the disciplined adherence to policy. So what is the greatest remaining vulnerability in this whole system? Is it ongoing training, system maintenance, or the human response that we are trying to coordinate.
A fitting challenge.
Thanks for listening. We will continue to talk about security and technology. See you in the next episode.